right, so we just started the recording. For people that will be watching in the future, we just covered basically domains and services, domain representing the business, service representing a subpart of the business, and it implements some specific functionality as part of a domain. And we were just talking about scalability versus elasticity. Elasticity being about responsiveness, being how quick can you scale. And the example, the image that we have here is an example of a distributed system. So this could be like Spark, for example. I think this is like, basically a classic Spark diagram, where you could think of these as servers where you have, basically workers and a leader. So the leader will give work to each of the workers and coordinate their work. It doesn't have to be that. I think you could have it you could have nodes on one computer, on one server. But the nature of distributed computing, distributed systems, is having multiple servers. And yeah, that would be horizontal scaling. So you're adding more instances, more servers, rather than increasing the capacity of a single server. And I guess to cover the last part, designing for failure, the obvious advantage here is that if you only have one server and that server goes down, then you're in trouble. You could, get it back up in the future, but yeah, it would be really bad if, for your business, if it's not available and people will go elsewhere. But if you're distributed, then you can have failover instances, and people might notice a slowdown. They might not even notice a slowdown if you get your new servers on like really quick. So that's the designing for failure. Okay, so the next idea is, hold on, before we go on. Oh, Bikram has a question. Okay, yeah, sure, go ahead, Bikram.
Yeah. Will this ping? I need my headphones, sorry. Yeah, otherwise I'm just echoing. Yeah, I'll just
Oh, hold on. Give me 1 second. I think it's because I'm not using headphones. So, 1 second. All right. Headphones. Okay, go ahead.
Yeah, so I guess like on scalability, like especially on the previous slide, like my question is like every time I have tried something like this, almost every time, especially if we are on the SQL based system, like a backing database, like we always run into the issue of like, oh, the database cannot scale like horizontally as the normal, like our application servers can scale. Like, so, like, is there anything like upcoming based on that, or do we need to think about it separately?
Well, I just want to make sure I understand your question. You're saying you've run into issues where your database doesn't scale.
Yeah.
And like either horizontal or vertical scaling don't work?
Vertical usually works because you can do it only till a limit, but horizontal doesn't work because you can horizontally scale 2x, 3x very quickly on the application side, but the database is like, I can't keep up. So it's just one server.
Okay. Is this, I guess the first question would be, is it a transaction database or an analytical database? Like,
That's transactional, always. Like a normal RDB miss.
Oh, okay. And you're querying it, and that's where you're running into issues, or it just can't ingest like all the transactions that's happening to it, that are occurring?
Yep. It just can't like keep up with the spike of like the number of queries, both inserts and updates, like when there's like heavy usage. So either like you have to over provision the database always a lot, or
yeah, I mean, I guess just the first thing would be like, and you might already be doing this, but you shouldn't be running analytical queries on a on an OLTP database, on a transaction database. But if you're saying that you just have a lot of transactions that are happening and it can't, you can't ingest those into the database fast enough. I don't know. I don't. It's a good question. I would just I would say like, can't really give much of a better answer than make sure you have enough RAM and CPU and storage, which should be vertical scaling. In terms of an OLTP database, yeah, you probably can. I think you can. In fact, I'm basically positive that you can horizontally scale that, which is obviously introduces a lot of complexity. But yeah, like, yeah, I guess my answer is just horizontal or vertical scaling should work. But if anyone wants to chime in and give their own answer, feel free to. I think someone else had a question or just raised their hand. Something with a Y. Yeah. Yeah. Y SS Isirki. What's the good for these? Yeah, sure. Okay. Isirki, did you have a question? Okay, feel free to post in the Q&A if you want. If not, we'll just continue. But yeah, I don't know, Bikram, did that answer your question?
To an extent, but yeah, I think I need to dive a bit deep into this.
Yeah.
Problem.
Yeah. Probably at this level we're covering the concepts just at a high level. Scaling a transactional database, I'm sure there's a lot of more detail. But at least at this level that we're covering, I can't give you a better answer than just in general horizontal or vertical scaling. I don't know if there's any other principles that we're equipped with at this point. But no, great question. Thanks for answering it. Sorry, thanks for asking it. But yeah, if we have time at the end, I'm happy to discuss it more. So, all right, let's continue. So, coupling, tight versus loose coupling, and then it comes in the conversation of coupling can be seen in tiers and monoliths, microservices. So tight coupling is what it sounds like. Everything is tight. Everything depends on everything else. So every part of a domain and service, which we discussed, is vitally dependent upon every other domain and service. And loose is they're not. They're decentralized. Things are independent. Yeah. So the independent aspect, I'm sure probably it sounds like loose coupling is better, and it is. The authors say pragmatically use loose coupling as an ideal, meaning, yeah, loose coupling is better, but like there are instances, there are examples where tight coupling is fine. Like the classic example just being like if you're a startup, if you're just getting something off the ground, then your main focus is getting something that works. So just it's fine to just throw something together. It's fine to often start with a monolith, and then once you have it working, then you can transition and just care about scale. So yeah, loose coupling is an ideal. I just wrote, remember Amazon's API mandate? That was like principle 5 of the example there was just at some point in Amazon's evolution, presumably actually after they had started with tight coupling and a monolith, Jeff Bezos sent out a mandate that every team had to have an API, like had to expose their data via an API. So it's basically just here's a consistent way that every other team can access our data, and it allows teams to be independent of each other because like it's basically a team telling every other team like this is all you have to know about our data. We'll take care of what's going on under the hood, but you can expect to be able to pull this data like this. And then at a certain point APIs will change too, but for other teams they really have to know a lot less about what you're doing. I heard a question, but let me just finish the slide. So coupling can be technical or domain. So the solution for technical coupling is multi-tier architecture. So technical coupling would be like you have, and I think there might be an example on the next slide. Yeah, so technical coupling would be architectural tiers. So on the left, you have technical coupling. You have one server with your database and your application logic. So they're literally on the same server. Your code and your database are together. If that server goes down, then like if your database has an issue, then your application will also go down, and vice versa, I think, as well. Whereas on the right, you have where they're separated. Actually, so they are hierarchical. So if your data layer has an issue, then it actually would affect your application and your presentation layer because they depend on it. But if your presentation layer has an issue, that could just be isolated to it, and your application layer and your data layer don't necessarily have to be affected by it. So this is an example of loose versus tight technical coupling. Whereas you can also have domain coupling, where, to go back to domains and services, you could have like your sales and your accounting stuff like just thrown in together, and it's unclear where one domain ends and one begins. And the solution for that is just model data properly, and then write your code and build your services around that. Whereas the solution for technical coupling is a multi-tier architecture, like you can see here. Yeah, did someone have a question? I heard the ding. Coupling in a startup is a huge trap. Yeah, it is, but you can't have the perfect architecture when you start. So, like clean code is important, but you have to write. Speed is also important. So it's that classic trade-off. Okay. Next, we get to monoliths versus microservices, which continues the coupling conversation. So an extremely monolithic architecture runs all functionality inside a single code base. Yeah, and this can even be just one server, one computer, potentially co-locating a database on the same host server. Right, exactly what I just said. And then on the right, microservices, it's more complicated, but it's a lot more resilient. If the service and the database supporting that service on the right go down, nothing else has to be affected by it. Potentially they can be, but ideally everything is isolated. And yeah, it's pretty straightforward. Monoliths are tightly coupled, and microservices aren't. Yeah, we'll get a little more complicated because you can have, in the examples we've talked about so far, monolith, like this monolith exists on one server, but it doesn't have to. So, you can have in distributed computing, you have multiple servers. So you can have a monolith, a distributed monolith, which is a very interesting thing because it's a monolith, so it's tightly coupled, but it's distributed, so it's less tightly coupled. He just mentions that in the chapter as a strange new creature. But so things can get more complicated, but these are good high-level ideas to have. Okay. Anyone have any questions at this point? Okay, let's continue. User access, single versus multi-tenant. So this is this relates to like it's I guess more relevant to cloud services. Like, so the authors say in some sense all cloud services are multi-tenant, although this multi-tenancy occurs at various grains. And then I've added the table, the server at the data center level. So that means like, where is your data and code, your application living? Is it living together with other companies' data and code? So if you have your own infrastructure, if you have your own database and servers, then it's single tenant. You own it. I guess unless you're hosting other companies on your stuff is your hardware is dedicated to your company, so you don't have to worry about about accidentally mixing up other companies' data with your data. But if you're a cloud provider like AWS, then you have like racks and racks of servers, and you're going to have different companies likely on the same server, unless those companies specifically ask for their own dedicated hardware, and they'll pay you for that. But yeah, companies can have, and I'll come back to this in a second, actually. So there's two factors to be aware of in multi-tenancy. One is performance. So you can imagine multiple companies being on the same server, and one company is just like using tons and tons of the resources on the server, the CPU or GPU cycles. And if you're AWS or the cloud provider, you charge them more for that, but they could still, I guess, potentially affect, just because they're using tons of resources, they can slow down the other companies that are on the same server using the same hardware. So that should be accounted for. And the other issue is security. So, if you're a company and you're storing multiple companies' data in the same table, maybe for your own purposes, maybe just because it's easier for you to have one table where you have multiple companies' data, and it makes it easy for you to run reports and to see how many different companies, just run aggregate data. You can imagine just like, I don't know, just thinking of an example on the fly, but let's say you're a company and let's say you sell things to multiple companies. You sell, I don't know, widgets to multiple companies. And in your database, you have like, which company bought how many units of the widget on which day. So company A bought five widgets on Sunday, and company B bought 5 widgets on Monday. If you accidentally return to company A that company B bought 5 widgets on Monday, that's terrible. And you're probably not gonna, but I guess more for company B than for company A, but company A will also not trust you after that with their data. So you have to implement the right views so that each company is only seeing their own data. So data can be stored in the same table for multiple companies, can be on the same server, and I guess it goes without saying that multiple companies will have data in the same data center. So that's what's meant by user access. Okay. Next, I guess we'll talk, we have event-driven architecture. So this is in contrast to what I said before is request. Oh, sorry. Let me take a look to see questions. Is single tenant expensive? Yes. Yeah. So single tenant can either be you purchase your own hardware and then you store only your own stuff on it, and that's expensive. That's the whole purpose of using the cloud, is to save you from doing that. But even within the cloud, like you can ask for your own dedicated hardware, but you're going to pay more for that. So it's definitely more expensive than multi-tenant. Yeah. So okay. So yeah, event-driven architecture is basically stuff happens, some state changes, and you do something in response to that. So an event can be a customer buys something, or you have a home security system and the alarm goes off. Like that's an alarm, that's a state change. Or yeah, just anything, something changes in the state. So there's a producer which produces the event and to be consumed by the consumer, and then it passes through a router. And event-driven architecture is associated with loose coupling because one event can be processed by multiple other services. So the event is decoupled from the service, you could say. Like in the example below, service 1 produces an event, and it's consumed by 2 different services. So service 2 and service 3 are consumers in this example. Service 1's the producer. It doesn't show the event router here. There could be one. I suppose you don't need one, but it's often helpful. And like, I guess the big service that you might use in this case would be Kafka, like that. That's a message router or message queue. Yeah, so that's what implements event-driven architecture in response, as opposed to request-driven architecture, which is like you send a request. One service is, I guess, directly telling another service what it wants, or you poll at specific times. Like, it's less immediate, whereas events are more in real time, rather than at set times. Yeah. Okay. And then the last part, before we get to so we're on concepts right now, and we'll get to applications or real examples of these concepts. Brownfield versus greenfield projects. These are pretty straightforward. Brownfield is like you have an existing project and you want to refactor it, make it better. And people have made choices about the architecture in the past, and you're trying to improve them. So the authors stress a lot, don't do like I think they call it a big bang overhaul. Like you just do everything all at one time, because you're going to overwhelm yourself most likely. So take a gradual approach, and show that like don't move on to the next thing before you've successfully demonstrated that you've replaced one thing. They call it the strangler pattern. Greenfield is you have a totally new project. You're building something totally new. You're not constrained by any choices that people have made in the past. The temptation here is to use the latest and greatest tools. But you could. It is, while you should be using like good tools, that doesn't necessarily mean that they're the latest. Whatever, like if you know an old language, then use that. Then if it'll allow you to meet the requirements faster, then do that. Unless, for example, you think for whatever reason like it's going to become outdated like the second after you build it. And then they'll need to do a brownfield project. So yeah, the idea is pretty simple. Although I myself, like I only heard the word greenfield, I don't know, like a year ago, and I didn't know what it meant. I mean, I knew what it meant, but I didn't know what it meant. I didn't know that brownfield was the opposite. So yeah, I mean, now that I'm thinking about it, yeah, greenfield is like a fresh field, whereas brown is, I guess, it's been withered by the sun and it's dry. So yeah, that's the idea. Pretty straightforward. Okay. Now we're halfway through. So if anyone has any questions, feel free to unmute or just post it in the channel. Oh wow, there's been this whole conversation. Oracle DB is AWS, single tenant, yeah, manager. Okay, you guys are, looks like you're successfully answering each other's questions. Okay. So those are the high-level architecture concepts. Now we're going to get into more, I guess, concrete examples of how those concepts are applied. So this is what we're going to discuss: data warehouses, data lakes, data lakehouse, which is a combination of the previous two, the modern data stack, Lambda architecture, Cap architecture, the data flow model, and we're not going to talk about architecture for IoT, Internet of Things, and the data mesh, even though the authors do talk about it. I just think it's less relevant for most people. And yeah, I mean, it's also not that much to say about them in the book. So without further ado, talk about data warehouse. This is like probably the most. This is very fundamental, very important. Probably almost everyone has dealt with data warehouse. So it's a centralized data hub used for reporting and analysis. Data in the warehouse is typically highly formatted and structured for analytics use cases. So this is in contrast to a database, which briefly discussed earlier with Bikram. A database is associated with OLTP, online transaction processing, and it stores like the current state of your business. Whereas data warehouse has a lot more data because it stores current and past state, and is used for analysis. So that would be on OLAP, online analytics processing. Yeah, So I mean, I guess you could call a data warehouse a kind of database, but it's bigger and there's more data. But I guess they're both structured, highly structured. So yeah, so two main characteristics of data warehouse. It separates OLAP from production. Yeah, so basically what I just said. And it centralizes and organizes data. Okay, more, yeah. So ETL versus ELT. So ETL stands for extract, transform, load versus extract, load, transform. So ELT is a more modern thing. Like ETL was what existed, was the pattern that existed of ingesting and loading and transforming data for decades. And now that storage is cheap in the cloud, we're able to basically load all the data that we generate without first transforming it, and we can transform it in the cloud because we don't have to worry. Like, there's no limit on how much data you can store, essentially. And not only is storage cheap, but we also have the compute ability that we didn't have before. So you can actually process that data. So whether the transform happens before the load or after the load is now an option that you can choose. Yeah, so cloud data warehouses are becoming more like data lakes. There's a convergence there happening. And that's because, so talk about this in a second, data warehouses have certain advantages over data lakes, but the new data lakehouse, which is a term that Databricks came up with, and the authors also use the word data platform, takes the best of both worlds. So I'll cover that in a second. Here you can see ETL versus ELT. In ETL, which is the older pattern, you have data sources. In the ETL system, I guess this is where compute happens, and you load your data from the data source. You do your transformations, and it's a funnel, so you have less data at the end, and then you load that into your data warehouse, and then from there it can go to data marts. Whereas in the newer paradigm, you take everything from your data sources. You in the first arrows, you're not doing anything other than dumping it into staging, which is a part of your data warehouse. So it's a little confusing because the second arrow is within the data warehouse. The second arrow represents your transformations, and then from there you put it into your data marts. So they should both be pretty straightforward. Yeah, and so what is a data mart? It's a refined subset of a data warehouse, designed to serve analytics and reporting, focused on a single sub-organization, department, or line of business. So, it can be your sales data mart and your accounting data mart. And there's two advantages of a data mart. One is just for business purposes, it's more clear, like, that each department will have their own subset of data. But it also allows you to have better and faster processing time, because, like, if I'm sales and I want to apply a certain transformation to data, like, I don't have to do it on all the data that exists in the company. I only have to do it to the data that I care about. So it just makes sense to subset the data in that way as well. Okay, so then we get to data lake, which is a newer thing. Data lake, the basic idea behind it, how it's different from the traditional data warehouse, which has existed since like the 1980s, is separating storage and compute. And now we have basically unlimited of each. Like, you could think of in AWS, you have S3. Azure and GCP have their own versions, but I'm not sure what they're called. GCP storage, maybe, clouds and blob storage. Yeah, so you essentially have unlimited of each. I mean, if you have the money. So that was the idea. In a data warehouse, storage and compute, it's in a traditional data warehouse, storage and compute are coupled. In data lake, they're not. Data warehouses still beat data lakes, at least first generation data lakes, in a few areas. One being that data manipulation language operations. So something like as simple as a join was very cumbersome to do in data lakes, where you're writing MapReduce. I think almost like very few people use MapReduce anymore. But in SQL, a join is pretty simple to do. SQL is the language of data warehouses. Data MapReduce was the language of data lakes. So it was just very complicated to do stuff there. Data management was hard in data lakes, and MapReduce is an open source language, and just things, the authors talk about how things were often complicated. Like companies came around that would wrap open source languages, and I would try and make it easier for you to use open source. But it was still complicated, and it cost a lot of money to hire people that knew MapReduce very well. So data lakes were still very expensive to use. That now we have convergence of data warehouses and data lakes. The data lakehouse being example of that, or you can also call it a data platform, and you get the best of both worlds. So you get the controls, data management, and data structures of a data warehouse with the separation of compute and storage of the data lake. And compute can be, you can choose whatever query and transformation engines you want of the data lake. Okay, so just looking at the questions. So what do people say? SQL for transformation. See, what is the various considerations to decide between ETLs versus ELT? I mean, now, like, you should use ELT unless you're limited by space. Like, yeah, I think ELT has replaced ETL, unless for whatever reason you're still using a data warehouse and you're limited. And like, I don't know, it's not a cloud data warehouse. Well, okay, yeah. Yeah, Bikram answered it perfectly. Okay. Concepts. Okay, Bikram says every time I've seen a data lake, it's weird to make me and go to the data. Yeah, and the authors talk about how the problem with the data lake can just be, and what happened the first time with the first generation of them was you just had massive amounts of data that didn't end up being used. So, and I saw this on LinkedIn the other day too. Someone else talked about this, just that the vast majority of data in Snowflake or in any data warehouse or data lake isn't being used. And, the author's point was just like, as a data engineer, and this is an idea that will come up time and again, just try and focus, find the things that really drive impact. Like there's the classic 80-20 rule. You can get 80% of the results with 20% of the effort or the resources. But like in a data warehouse, it could even be more. It could be like, 5% of your data is really what's important. And just find that 5% and work on that. Yeah, so that's data lake and data lakehouse. At this point, we're like 3/4 of the way through. Okay, the modern data stack is some people. In fact, the author of this book says that like kind of the modern data stack is dead. Not really, but like his point is just that it was a very hyped thing. Basically, the modern data stack is like a set of tools and capabilities that are modular. Like rather than having one monolith, one platform that does everything, today you can do like, oh, I want my transformations in the lake to be with dbt, and then I want my visualizations to be with Looker or Tableau or Power BI, and I'm going to use Spark for my batch layer and Flink for my streaming layer, and you can just like pick like a lot of different tools. That's what it means fundamentally. So yeah, the point is to reduce complexity, increase modularization. Plug and play can be with like no-code tools like Fivetran, which is in extract and load platform. I think it also does transformation, so you get that too. But you don't have to. It has no code or low code capabilities. So, and easy to understand pricing. That's I guess an ideal. I don't know if that's always done in practice. So yeah, so data sources, cloud-based data connector and ingestion. Fivetran would be a great example of that. Then you go into your cloud data warehouse. It can be Redshift for AWS or Azure, GCP, BigQuery would be their cloud data warehouse, or Snowflake or Databricks. Those are the top 5 market leaders. And then BI and visualization, and the tools like Tableau, Looker, Power BI would be the leading examples there. Okay, that's really all there is to say about that. Okay, so we get to the last big idea that I'm going to talk about, which is different kinds of architectures. The question is, if you have both batch data is data that's loaded in periodically, as opposed to streaming, which is data that comes in as soon as it's available. How do you manage both in a single architecture? So there's 2 traditional ways that you can do that. The first and the older kind is Lambda. So that is, you have them both happening in tandem. You have Lambda, you have batch and streaming processes that you handle them separately, and then you only combine them at the end when someone wants that data, when someone asks, has a query about that data. Actually, even then, I think you might still keep them separate. But like, I guess the fundamental point is that you're treating them separately throughout your process. Whereas in Kappa architecture, everything is streaming. And Kappa's newer, I think it's been around since 2014. So you treat everything as streaming, which makes sense because streaming is more fundamental than batch. There's 2 problems with Kappa, which is that it's hard to do. Companies don't really know how to do it, and it's expensive to do. So really only do streaming if you need it. In keeping with the big theme of the book, don't overcomplicate things. So yeah, so let's see an example of Lambda architecture, what it looks like. So you have your source systems. You're in your data warehouse. You have you're handling stream data and batch data separately, and then when someone at the end makes a query, like that's routed to the relevant relevant source to get that data. But there's separate code handling the streaming data and separate code handling the batch data. So that's the downside of it. It increases the code. In streaming, you're simplifying things. You're treating batch as a subset of streaming, which is a step in the right direction. But even Kappa is limited in that although the query and storage layer is unified, under the hood, you still need different tools for collecting real-time stats and running batch jobs. So it's almost there. You've almost completely unified batch and streaming, but you're still using slightly separate, like you've partially unified them, but you haven't completely unified them. So in response, Google developed the data flow model, which is a model, and it's been implemented in, I guess, 3 different Apache frameworks: Beam, Flink, and Spark. And yeah, basically, batch is bounded stream data and streams, and now you only need one code base. The same code can handle batch and streaming data, whereas in certainly Lambda, but also in Kappa, it can't. Okay, so that's that. Let's just conclude, like the authors conclude with like the chapter on data architecture with who's involved with designing data architecture. Ideally, you have a designated data architect. Like some companies are big enough to do that. But if not, then it's going to be the data engineers that do it. And the line between architecture and engineering is blurring. And they say the days of ivory tower data architecture is gone. So you have to know the details. You have to be hands-on, and you can't architect without, I guess, like, I was going to say you can't architect without coding. I guess you can, but you need to. It certainly helps to know coding and just to be involved in the weeds. Okay, so that's everything at high level. We covered a lot of different ideas and concepts. If anyone has any questions, feel free to ask them. Bitcoin says BigQuery is an implementation of a data warehouse. Yeah, it's a data warehouse. Diff between. Yeah, go ahead, Vikram.
Yeah. So, like, especially in our current environment, where let's say we do not have too much of like data architects, right? Which I've seen. So, how do you think about like solving the problem of like different teams ending up with different nomenclatures for the same thing, or even worse, the same term meaning different things for like different parts of the company, and then like you have a mess in the whole entire data. So how, like, what are good strategies to avoid that?
To avoid what? Different terminology?
Yeah, like different teams when they're developing their own data architecture, like for their part. So they have like they're using different terminologies altogether. Like,
Can you give an example?
so example, like in one of my previous company. So based on like whom you talk to, so we were doing some clinical trials. So based on whom we talk to, the word study would mean like completely different things. And in our data warehouse, a lot of places we had like something called, okay, this is a physical study. Now, how is someone like going to figure out, okay, what does it mean? Like in this, like, what's the meaning of study here? Because it's like that term is like now messed up completely.
Oh, are you talking about like business definitions? Yeah, just like a term that's specific to the business, and different teams might use that term in different ways.
Yeah, like usually with like a data architect, you'd like spot all those things, like usually he or she. But like without that, that coordination like becomes very difficult.
Right. I mean, I think so. They do mention not. It's either in this chapter or in the previous one. That I think that's the role of data catalogs. I think it's in the previous one, chapter 2, that you are supposed to like like you can define what terms mean, and I think that would be done in a data catalog. So uh, and then if different team, I mean, I suppose different teams can have their own data catalog, so two teams can define the same term in different ways, and then you can just look at that team's data catalog. But yeah, I mean, ideally they wouldn't. Yeah, I don't know if there's a way around that. I think that's what Lenny says in the comments. That's the way it is with terms. You have to define what it is. Yeah, so I don't know. Like, I guess you could go to them and make your case for why you think that the term should mean what you want. Or maybe they convince you that they're right. And then even if one of you agrees that the other is right, you have to go and like refactor, your code base, which hopefully isn't too much trouble to use a different term.
I
Yeah.
can. I can chime in.
Yeah.
So you kind of write about data catalog. So I can from in my previous company, we had sort of a similar challenge, because multiple teams were like there were data being used across by different teams, and they were kind of naming it differently. And so there was no, I would say, single repository, or I would say even like source of truth, or like what data meant and stuff. So what we ended up doing was we ended up building like a data catalog. And this wasn't a data architect who did that. uh, it was kind of a TPM, I would say, worked with the engineering leads when we kind of listed down what are the various, I would say, like data systems, whatever they have been using, what is upstream, downstream on the source, and the terminologies, and like I would say how frequently they're getting the data and stuff. So what finally ended up happening is it was like a big master data list, a list of all the data sources with the metadata sort of captured. And the end goal was to sort of build like I would say, like a one source, which is probably like a, I don't know, maybe like a data lake or platform. But I mean, I'm not part of the organization. So we sort of did like this activity of cataloging and trying to document the data and the metadata of it. So that way we could, while talking to while two teams, different teams were talking, they could sort of refer that and gain some alignment. I hope that's helpful.
Yeah. Well, I mean, Bikram, do you find that helpful?
Yes. I
Okay.
guess I just need to figure out how to find my tab first, but yeah.
Yeah, so I posted a quote from page 53 of the book. So in that section, he's talking about metadata. So, and it's quite detailed because there's four different kinds of metadata he talks about. The first being business metadata. So he says, like, he's using the example of a data engineer may be tasked with creating a data pipeline for customer sales data. But what is a customer? Is it someone who's purchased in the last 90 days or someone who's purchased at any time the business has been open? So different teams might have different definitions of a customer, for example. So data engineer would use the correct data to refer to business metadata. So either a data dictionary, or data catalog. Yeah, so and hopefully, again, like different teams can use different definitions, but if you have a data catalog, if each team has their own catalog, then you can see how each team is using it. Yeah, so I don't know, hopefully that's relevant. Yeah.
I think thinking about it a bit more, something that's really coming to mind is like we used to have a data catalog in Confluence. So every time someone would like make a change of the actual data schema something, the Confluence was like always many months out of date at any given point, easily. So the way I'm thinking about it right now is maybe like make the data catalog as a part of the code so that like a CI action can check like if the data catalog is also updated, if anyone is changing any data schema or data architecture, maybe that might be a way to go around.
If anyone changes the data, yeah, you're saying the documentation's often out of date.
Yeah.
Yeah.
Or like not even there for like a lot of part of the data warehouse.
Yeah. Yeah. But wait, like, now you're talking about people changing the definition on the same team or on different teams?
Or on different teams. Like for example, someone started like a new part in the data warehouse. They added 10 tables, which means
Right.
something, but like it's not cataloged. So
Right.
yeah, that whole thing like becomes a mess. Like no one knows what it means otherwise.
Right. Right.
Yeah.
Yeah, I mean, I don't know what the solution for that is other than preventing people from, like, I suppose we're also not talking about like sandbox or like a development environment. You're talking like someone is using like a like they're using definition in a different way. and now
Yeah,
that's confusing other people. But I guess ideally they shouldn't get to that point where they can like push that beyond development.
Yeah.
But real life is complicated. So
I think it kind of depends on what tools you're using for data cataloging, because I heard you just mentioned Confluence, right? So that's a very manual and separate process from your code.
Yeah.
Some tools let you put it within the code. In DBT, it's very common to include it right in your code. Sometimes people put it in the comments of the table structures, and that might propagate somewhere into a visible tool. So it depends on how integrated your process is with code itself. Which is the best for making sure they're in sync.
Yep.
yeah, and that's also, I think that also relates to the idea of data lineage. And like yeah, so data lineage is like, where did this piece of data come from? So it's not the same idea, but there's also a lot of companies now that I think are involved in that. Like the data catalog company that I'm familiar with Confluence, obviously I use it. Calibra is like one that my company uses for data cataloging, although I think that's also manually updated. But I think there are a lot of companies now that are trying to like automate the data cataloging and like use, AI LLMs to have that so it's automatically updated. Yeah, I guess the definitions be automatically updated. But anyways, you're gonna say something, Vikram?
No, I think like making like, as long as like if there are tools which has like an integrated process, I think that solves a lot of things. Yeah.
Okay.
Yep.
All right. So I think I succeeded in having us finish finished at 9:53, so in under 50 minutes. I did prepare 5 questions. For those that want to stick around, there's a lot fewer of us than there were last week. So we can I'll just go with the question, and you guys can just put your answers directly in. We can keep this pretty informal. I also just kind of like we're just doing 5 questions. Okay. Yeah. What's the primary benefit of an event-driven architecture over a request/polling architecture in distributed systems? A, completely eliminates the need for databases in the architecture. B, it ensures the components are more tightly coupled, improving data consistency. C, it enables components to asynchronously respond to events, improving scalability and responsiveness. Or D, it relies on periodic polling to ensure that all components have the latest data, improving reliability. More tightly improving data consistency. Yeah, okay, it's C. Yeah, I mean, D doesn't make sense because polling is literally the opposite of event-driven. A is like a non sequitur. I don't think you can have an architecture without databases unless like you're just, I don't know, using caches for everything. That's still like technically a database. B, yeah, event-driven architecture is associated with loose coupling, and I also don't think tight versus loose coupling has anything to do with data consistency. Okay. What is the key consideration for deciding between a greenfield and brownfield project approach? A, greenfield projects always require a larger initial investment than brownfield projects. B, brownfield projects offer more flexibility and technology choices compared to greenfield projects. C, the presence of existing infrastructure and systems that must be integrated or replaced can influence the choice between greenfield and brownfield. Or D, greenfield projects are less risky and quicker to deliver because they start from a clean slate. Yes, save your messages. Hold on. Vikram, are you saying that about something else? Save your message. Oh, you're talking about the previous question, maybe?
Yeah.
Yeah. Right. Oh, that relates to event-driven architecture. I guess that would be Q. Okay. Anyways, all right. I think on A we also had Shubhashri. So maybe I'll wait for them to answer. We already have disagreement here. Oh wow, we have three different answers. Yeah, I was thinking that it's C, it's Shubhashri. So, but let's hear, like, we'll see what different people are thinking. So, okay, let's start with A, which Lenny said. Greenfield projects always require a larger initial investment. I mean, certainly since you're starting from scratch, I hear that. Although I guess I would think it depends on the project as well.
Yeah, I just wasn't really sure. I didn't have
Yeah.
much conviction on this one.
Yeah. So that's why I wouldn't go with that one. No one said B. Yeah, no, that's the one that they don't offer. So good job on not choosing that one. C, the presence of existing infrastructure must be integrated or replaced. Yeah, so I mean, I guess, like, and yeah, they also the authors talk about this in the context of, like, I think it's the context of a monolith. Like, if you have something that's just so tightly coupled, then, like, it might just make sense to, like, start building a parallel architecture that's loosely coupled from the start rather than trying to extract things. So that, I think, is an example of a project that could be brownfield or greenfield. And does it depend on the presence? Yeah, I guess that depends on the extent of the coupling. Yeah. So I think that's, like, the example that relates to this question. And then greenfield projects are less risky and quicker. I mean, I wouldn't think that they're. No, I would say they're probably more risky. I mean, obviously it depends on how much, like, a brownfield project can just be like, replace this, like, one service, and, like, you can be done very quickly. Whereas greenfield can be like, we have this massive project we're building from scratch. So those also, like, a lot of these questions are just, it depends. A lot of these choices. Yeah. I guess just the tip here is that, like, the ones the language that hedges is generally the right one. Right? A and D, but, like, say always, and are less risky. They're definitive. So yeah. Okay. How does Capita architecture fundamentally differ in a sparse data processing compared to the Lambda architecture? So A processes all data through a single path, whether it is real time or batch, eliminating the need for a separate batch layer. B relies exclusively on batch, both real time and historical data analysis. C, it introduces a third layer dedicated to machine learning, model training, or D, it emphasizes immutable data storage in the serving layer. Yeah. Okay. Yeah, I never tried that in university on multiple choice questions. Bikram just, like, crossing out and, like, saying it's not this answer. Well, I guess I did, because just in classical multiple choice, you use process of elimination. But yeah, I wouldn't give you anything for that. So yeah, I think C and D are, like, again, like, not relevant. Yeah, I mean, there's no third layer, and didn't talk about ML at all. And then in Cap architecture, well, there is storage underlying everything, but we didn't talk about immutable data storage. Yeah, and I guess it's I guess it's all immutable. No, whatever. It's not relevant. Yeah. Okay. Anyways, and then B is the opposite. It relies exclusively on streaming, and then yeah, A is a process all data through a single path. Eliminating the need for a separate batch layer, which would be what Lambda architecture is. So they do say that Lambda is like, well, I was going to say they say it's outdated. They don't say it's outdated. They say it's not ideal, but I think they do. I think they imply that most companies are using Lambda architecture because most companies are using batch. And yeah, like, yeah. Okay, that's that. Good job. Oh, this one was, we talked about this a bit last time. This is my monoliths and microservices question. So why did Amazon Prime Video abandon their microservice architecture for their video quality analysis tool? Was it A, microservices offered better performance, but were too complex to manage? B, the microservices approach became too expensive and created bottlenecks? C, they wanted to leverage the benefits of serverless computing, which weren't compatible with microservices? Or D, security concerns arose due to the distributed nature of microservices? Okay, so you guys think Bikram says A, Lenny says B, and Shubhashri, where are you? Yes. B. Oh wait, you guys all say B now. Okay. Yeah, that's right. Yeah. I mean, A is an interesting one because microservices generally do offer better well, yeah, I want to say they generally do offer better performance, but they didn't in this case, and were too complex to manage. I don't think the issue is that they were too, well, I guess the bottlenecks you could say were the complexity, and it wasn't like the big headline there was that they saved 90% of their costs. So that's definitely the too expensive part. I think like A is almost right. Like I just think B is like more right. Yeah.
Yeah, I don't think A is right even in performance because you still like they had to pay a lot of cost in deserialization, which should like technically bring down the performance anyway, like deserialize and deserialize. And like even like in all microservices that we do have the cost anyway. So yeah, like performance wise microservices may not be always like best. It's just like easier to change.
Right. You're saying because of microservices, you have serialization and deserialization. It introduced right, like from one service to another, you have to serialize and deserialize, which makes it take longer. So and therefore slows down the performance. Yeah. Okay. But like what was unique about it? And now I guess I'm asking you this question. What was like, because they're still using like microservices is still generally the better architecture to use for large systems. So like why is Prime Video unique?
So the thing that they were it was like a series of different analysis that they were doing.
Yeah.
Like analysis A, analysis B, analysis C, and like every time they would like serialize a video clip, then send to the next analysis microservice, then the next analysis microservice. So just serializing the video clip, it's expensive, like yeah.
Right.
And sending it across to yeah.
Right.
But if you have it in memory and then you can basically do all the checks one by one, you have the big object anyway. So
right. Makes sense.
I wouldn't say microservices as a general statement is always a better architecture. I'd consider it like as a more scalable architecture and more like it gives you the ability to modularize components like as you would like with teams, right? Like different teams can focus on different areas, but it in itself, each time you add an abstraction or a new communication between them, you have another thing to kind of manage, and so that's one thing that could be a downside, and another thing that could be a downside is how you communicate, like what the signature is between the two. Sometimes, like for example, in data pulls, a lot of times you run into like you have to get a row at a time or batch them into 50 or like any number. You have to batch a number of API calls. But sometimes, like if you could just give it like a list or something, the signature can constrain how you talk across one system to another. And if it doesn't provide you what you need, then it can make things a lot slower if you don't have good like if you can't control both ends of it. So sometimes the nature of having different teams and different priorities can make it actually a lot of overhead if you're not cooperating.
Right. Right. Yeah, no, I think that makes a lot of sense. Yeah, that's well put. Yeah, and then C and D are just not true because serverless computing is absolutely compatible with microservices. In fact, it's probably more relevant microservices like Lambda. AWS Lambda would be the classic example. And then, I mean, I suppose distributed computing is probably like intrinsically a little less secure because you're dealing with multiple servers and more data transit. But that wasn't the concern here. Yeah. Okay. All right. Last question. In data architecture, what distinguishes a data lake from a data warehouse? Okay, this is a pretty elementary question. Is it A, data lake primarily stores unstructured data, while data warehouse stores structured data, optimized for fast SQL queries. B, data lakes use ACID transactions for data integrity, whereas data warehouses do not. C, data warehouses are suitable for real-time data processing, unlike data lakes. Or D, only data lakes can store data in the petabyte range or higher. Right, Lenny's quick with the A. Right, Bikram, you want to answer? Just waiting for you. Okay, yeah, exactly. Yeah, I mean, I don't know about primarily stores unstructured data. I guess it can store any data. Yeah, and a data warehouse necessarily stores structured data. I've also seen semi-structured data, whatever that means. Maybe it means like JSON data. And yeah, SQL is the language of data warehouses. Bikram, you're saying BigQuery can scale to petabyte range. Snowflake also maybe, others can't. Oh, okay. Yeah. Okay. So those are, and like, I don't know, probably Redshift as well. No? I mean, I would assume they can, but
No, Redshift we tried.
oh, this is like from personal experience?
Yeah, Redshift like in after 10 TB, yeah, you start having issues.
Okay. That's
And another particular like interesting fact, I was doing like a Snowflake and Redshift POC comparison between them. For a lot of things where we optimized a lot for Redshift, like the schema, the queries, everything. Like Snowflake usually like just out of the box gave better performance than like Redshift almost always. Like
Oh,
you
that's
did not have to do any magic for it. Like I don't know.
You're using Snowflake for petabyte range? That's that'd be really expensive, right?
Yeah, petabyte range, yeah, but whatever you are using, it's going to be expensive. Like,
Well, so I've looked. Sometimes I've looked at comparing Snowflake and other tools, and I like Snowflake in that it's like pure SQL. It's very comfortable from a SQL perspective. But what I've seen so far is like the storage is dirt cheap. Like I don't even count that. But it's all on the compute. So because of the compute, like that, so far what I see is that can become very expensive, and you have a little bit less control of like how to optimize some of the things there. So in like really large scale things, I haven't actually ever tried BigQuery before, but in very high volume scenarios, I've mostly worked with like Spark, or when I've had to pick, I've also gone Spark, or Databricks. Use Spark just because of the cost.
yeah, I have seen that too. Like, just go with Spark. Like at that range, like the cost is still manageable.
Mhm.
Yeah, like even BigQuery also, like you pay for the compute. So
Wait, you're saying you guys are saying that Spark, like i.e. Databricks, is cheaper than Snowflake for compute?
yes,
Oh,
So
interesting.
yeah, for compute, I'm not sure how the storage cost is. I know for Snowflake, to me, it's very negligible how much. So like, what that means is like, if you're just ingesting it, like if you're just basically copying over data or doing, things have data sitting a long time, because sometimes people say, let's clean it up, right? Like let's delete some of this old stuff because, it costs money, but it doesn't cost that much money just to keep data. But what does cost money is all of your CPU. So that I'm much more careful of, like how much processing I'm doing. Where um, in a Spark kind of environment, including Databricks, I have a lot more control on what I can do to optimize um, what what my compute does. And Databricks itself also is really good at just they keep innovating things on from a performance perspective. But even if they weren't, I think it's cheaper compute.
Right. I mean, Snowflake has Snowpark, like, which I think is their version of Spark. But yeah, I don't know how much control they give you over the compute stuff.
Yeah, I mean it's hard to say. Like in when I was using it about a year ago, or less than that, um, that was it seemed very new, like not very flexible. Like they just had it, and you could put in you could put things in there, but it didn't really seem like an open, like you can put in libraries, and we would do some machine learning there, but I don't know. I didn't. It felt very constrained. I forgot why, but it's always very hard to say with technology, right? Because what doesn't work well or is expensive at one point, in a year or two, it could flip. So like they can fix things up or make it better. So as far as the latest state that I saw it was I didn't like using Snowpark at that point. Like trying it didn't seem uh it seemed like I was jumping through hoops to do it for some reason. I
Right.
can't remember exactly why.
Yeah, makes sense. Okay, well, with that, I think we're done. Thank you guys for both participating and allowing me to learn from you guys. Yeah, so like next time, we'll probably meet in 2, max 3 weeks, depending on my schedule gets crazy or busier. So yeah, so we have one more chapter until we're finished part 1. And the next chapter is choosing technologies across the data engineering lifecycle. We'll probably also split it up into 2 parts. So yeah, we'll talk about, cost optimization and business value, location, on-prem, cloud, hybrid cloud, blah, 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 building versus buy. There's a section on monolith versus modular. So I guess that's microservices again. Serverless versus servers. Yeah, so more good stuff. So yeah, I'll do that in 2 to 3 weeks. After we're done part 1, which again will be like another month and a half to 2 months at this rate, I want to get Joe Reese, who's the primary author, to come to like do an AMA on Taro. So that should be cool. Should get a lot of people for that. Yeah, but I appreciate you guys, being involved and yeah, allowing me to learn from you too. So hope you both have a great rest of your Sunday wherever you are. For me, it's 9:30, so and have got less sleep than normal this weekend, so I'm gonna go to sleep early. But yeah, thanks a lot for you guys joining.